Hello everyone and welcome to our new video training package of Abaqus. Ductile damage Abaqus model for 3D continuum element, a comprehensive and example-oriented package for advanced Abaqus and finite element users. Let's look at its content in this 20 minutes demo. If you want to start analyzing your projects in Abaqus, it is better to save your time by watching this demo and making your decision easier. This package contains one lesson and two workshops in more than 120 minutes. And here I will present you the first part of the lesson, and we can see some selected slides of them. In this presentation, we will learn about a continuous damage model that is used in ductile materials. This model will be based on the modified Lemaitre damage model. In this package, we will learn about the generalities of this model, and we will learn about the implementation of this model in Abaqus software, which is implemented by the VUMAT subroutine. And then we will get to know the capabilities of this model by presenting some examples. First, we will talk about damage mechanics. If a ductile object is under loading and plastic deformation and plastic strain occurs, eventually small cracks will appear in the microstructure of the material, which is caused by loading. And with increasing loading, these microcracks will grow, and after the growth of the microcracks, these microcracks will join together and macroscopic cracks will be created. And also with continued loading, macroscopic cracks will grow and will lead to the failure of the structure. In damage mechanics, macroscopic cracks are first modeled. In other words, the prediction of the occurrence of microcracks and their growth will be modeled. In damage mechanics, instead of getting into the physics of the problem, damage modeling is done by introducing parameters based on thermodynamics without involving the physics of the problem. How this will be done? We will talk about it in the next slides. The damage model we are considering here is a damage model that is used in the ductile materials and formable materials. If a ductile object is subjected to loading, it will initially behave elastically and then enter into plastic deformation and finally lead to failure. When we enter into plastic area, the damage happens when the plastic strain exceeds the threshold, and this damage starts to grow. The damage finally reaches a critical value and macroscopic cracks are created. The damage grows till eventually the structure fails. So it can be said that ductile damage predicts and models the appearance and growth of microcracks. In the current model, the damage is considered as isotropic damage and is represented by parameter D. If we want to model the behavior of an object under loading with considering the damage, we use this flowchart. When the object is loaded, we consider its structural equations. These structural equations can include elastic and plastic behavior. The initial conditions of the structure can be placed in these equations. It means material parameters affect elastic and plastic behavior. Here, the damage field is added to the problem by introducing the D parameter. And the damage parameter is considered as one of the parameters of the problem. When the structure is loaded, the structural equations are analyzed. Then the stress and strain field and internal variables, which are introduced as damage variables, are extracted. By obtaining the damage field in the problem and by comparing it with critical damage, it is possible to predict whether failure will occur in the material or not. So, when the damage reaches critical value, the occurrence of macroscopic cracks can be predicted, and with the continuation of loading and the growth of macroscopic cracks, the failure of the structure can be predicted. Now we want to know the amount of damage in more detail. If we consider a one-dimensional element and this element is subjected to loading, the effective cross-section of the structure is not the value of A, and it decreases due to the presence of microcracks. If the cross-section with the small cracks and holes is labeled AD, the effective cross-section can be considered as A minus AD. Therefore, to calculate the stress, which was in the form of the F divided by A in the classical mode, here we calculate the effective stress. It is denoted by tiled sigma, and the effective cross-section will be A minus AD. In other words, the effective cross-section is the one without the cross-section of the microcracks. If we factor the value of A from the denominator of this relationship, we determine the term AD divided by A with the parameter D and call it the damage parameter. It is clear that if the D parameter is equal to 0, it means that the cross-section of AD is equal to 0, which means that the crack has not yet been created. And if AD is equal to 1, it means that the cross-section of the microcracks covers the entire cross-section of the element and the failure of the structure occurs. According to the description, the value of F divided by A is the same as sigma. 1 minus AD divided by A will be equal 1 minus D. In other words, if we set F divided by A as sigma, the effective stress or tiled sigma will be equal to the value of the stress divided by 1 minus D. So, you can enter the damage parameter in the structural equations and put the tiled sigma value instead of the sigma anywhere, and replace the term sigma divided by 1 minus D with the effective sigma. So, the D parameter will be added to the structural equations, and we can predict the damage in the structure by calculating D. So it can be said that if the amount of damage is equal to 0, it means that no damage has occurred to this material. And if it is equal to 1, it means that AD covers the entire cross-section, and the structure can break into two separate parts. But in reality, the amount of damage reaches a critical value before reaching the value of 1, and the cross-section loses its loading tolerance and breaks suddenly. Therefore, this critical value will be less than 1, which will be between 0.2 and 0.5 for industrial materials. If the amount of damage reaches these numbers, this element will be separated and divided into two parts. In this package, the continuum damage mechanics framework for ductile materials is implemented and developed in Abaqus by VUMAT subroutine. Now we are going to the Lemaitre damage model. Lemaitre damage model is used for ductile materials. As a relationship, the damage growth is D dot, which is proportional to the accumulated plastic strain, and Y, which is known as the energy release rate and is a function of stresses. In the Y function, the ratio of sigma H and sigma equal is a very important ratio. This ratio is known as triaxiality and has an effect on damage growth. So it can be said that Lemaitre's model is actually an isotropic model, and its effective parameters are the accumulated plastic strain and the Y parameter, which includes stresses. And its most important parameter is the ratio of average stress to equivalent stress introduced as triaxial. As you can see, this model has both plastic strain and stress subordination. Therefore, it can be said that Lemaitre's model is a damage growth model that is a combination of stresses and strains. One of the limitations of this Lemaitre damage model is that it considers the effect of compressive and tensile loads as the same. This means when the equivalent stress is calculated in this part, it does not matter for this damage model is under tension or compression. In other words, compressive and tensile loading will have the same behavior on structural damage. To solve this problem, modified Lemaitre models have been introduced. In this way, when a structure is under tensile loading, cracks open and damage occurs. And damage growth happens. But if the same structure is under compressive loading, the cracks will close. But these cracks are not completely closed and damage is growing. But the damage growth is less than the tensile loading mode. This effect is known as the crack closure effect and reduces the speed of damage growth in compressive loads. For modeling, if the structure is under compressive loading, which you can see it in the figure on the right, the effective cross-section will not be A minus AD, and it is a bit more. The reason is that cracks will close under compressive loading. Therefore, it can be said that the effective cross-section of the structure is less than the total cross-section and is greater than the value of A minus AD. In this way, tilde A will be introduced, which is equal to A minus H multiplied by AD. H means the crack closing coefficient. As you can see, if the parameter H equals to 1, the effective cross-section would be A minus AD, which shows the same tensile and compressive behavior. And if the value of H is equal to 0 in the limit state, tilde A is equal to the value of A, which indicates that the entire cross-section of the cracks is closed in compression state. So we can say damage growth does not occur in the compression state. In experimental tests, it has been shown that in compressive loading, the value of H is of the order of 0.2. Therefore, if we enter the H parameter in the structural equations, the effect of closing the cracks can be seen in the modeling. In the slide, you see the modified Lemaitre model for ductile materials is fully explained, and the effective parameters are quantified. As you see, the effect of tensile and compressive loading is considered separately in this model. In this slide, in order to implement the ductile damage model, different techniques are explained. And finally, the most appropriate technique is introduced and used. In this slide, after choosing the appropriate algorithm and technique, its steps are explained and the relationships and conditions related to each step are given. In this demo, we will not go into the algorithm calculations, and in the main presentation, their calculations will be explained in detail. We can follow the formulation from the model that is in the references in this presentation. In order to be able to use this model in Abaqus software, we must implement this formulation by a subroutine called VUMAT. In this product, a proper explanation is given of VUMAT and its inputs and outputs. After that, we can start implementing the Lemaitre model with the equations related to the damage. Further details on this method are provided in the main presentation. In this slide, you can see the capabilities of the Lemaitre model in Abaqus. This slide shows an example of a notched cylinder under tensile loading. In the Lemaitre damage model, we should predict the maximum damage that is in the center of the structure, and we should see if our implementation shows this damage well or not. In this slide, you can see the simulation video. As can be seen, according to the initial assumption, the damage reaches its maximum in the middle of the structure. In this slide, the ultimate strain-stress diagram is drawn, and the difference between the diagrams when the damage behavior is not considered is well shown. The reason for difference in the graphs is well explained in the main presentation. Another practical example is shown in this slide. This structure is a cone structure, and the process of offsetting has taken place on it, and it is under compressive load. In this slide, the results are shown by entering the H parameter. In this slide, the results obtained from the Lemaitre damage model are shown. In the main presentation, these results are compared with the experimental test and proven. Another example can be considered is the issue of combining fracture mechanics with damage mechanics. In other words, when a structure is under loading and the damage reaches critical damage, the damaged area cannot resist and a macroscopic crack is created. The next example is about the direct extrusion process. The material is placed in a mold and force is applied to it by a ramp. And the material passes through the mold and the diameter is reduced in the material, so the cross-section is reduced. When the material passes through the mold, small cracks may be created inside, which is mentioned in this slide. Experimental tests show that due to the reduction of the cross-section and angle of the mold, two safe zones and an area where cracks are created are obtained, which is explained in the main presentation. In this slide, the simulation is done and its output is shown. This simulation can be compared with the experimental example. Finally, it can be said that if this modeling was done with the classical Lemaitre model, only marginal cracks would be shown, but here, using the modified Lemaitre model, the central cracks are also visible. And it is closer to the experimental results. By getting the full version of this tutorial, you can improve your final results to add value to your research. Good luck! I hope you have got enough information about this package, but don't worry at all. If you have any questions about this tutorial, ask us via support@caeassistant.com.